Well, we're very pleased to admit Vassily Manturov to one of our talks, and he's going to talk on virtual knot methods. I thought it was algebraic topology, but it seems to be classical topology, but I guess.
Okay, thank you very much. I'm honored to be here, and I'm really happy to give a talk at this seminar when we have so many famous people, and really I should have mentioned not just Roger and Lou, but possibly many of you, so I apologize for not having mentioned all of you, so thank you very much. And today I'm going to talk about some methods we have for about 10 years, parity and pictures and so on. Here are some preliminary things. So actually we deal with frame for graphs. So these are graphs which appear as projections of classical knots. However, I don't want to use the whole structure. Actually, preliminarily, I don't want to make any distinction between over-under, and neither I'm going to make a distinction between right and left neighbors. The only thing I would like to keep track of is the opposite edge relation. So I want to deal with those. And actually, I want to consider these frame graphs as projections of virtual knots. And in fact, I want just completely to disregard virtual crossings completely. So of course, I will make a distinction between knots and links. So if I have a two-component link, say, then I just look at its unicursal components. So this is usual. And now I define the notion of free links and free knots. And here I should give credit to Turaev, who first defined them as homotopy classes of Gauss words. I guess it was for free knots. So he was doing some formal definition of words modulo Reidemeister moves without any further bits of information as we have for Gauss diagrams. No right numbers, no arrows, just something free. And in fact, when I first disproved Turaev conjecture that they had to be all trivial, I constructed some invariants which were picture valued. So actually, instead of having polynomials or groups or whatever, I was constructing invariants which were valued in diagrams with coefficients. And now I want to argue that we can do something similar. And actually, I will not concentrate on everything because of the lack of time. So I will give a series of talks here and possibly elsewhere. And here are just Reidemeister moves for chord diagrams. And we can say that I'm lazy and I don't want to mention any over, under, plus, minus, and arrow directions. So, okay, so these are moves for free knots. And actually for free links, we have the same, but on different circles. Okay, and this is the general research plan, not only for today, but actually for maybe a year or maybe several months or maybe several years. Okay, so actually this will work for classical knots, but I have to find some parity, and I will say some words about how we can get some parity for classical links. We can go this way, or possibly you can find a detour how to get to free knots some other way. And the result I'm going to present today will be something when we get free knot invariants valued in free groups. And this will be similar to picture valued invariants. And actually, I want to have some general principle. I want to make my invariants non-commutative. So actually, what do we usually have for invariants in some classical topology? Actually, we want to count some numbers. And possibly we can give some flavor to these numbers. For example, we can say, okay, we are looking at intersections between some moduli spaces. So we can have some moduli space which turns out to be a sort of manifold, and we intersect it with another manifold so that the dimensions fit nicely, and we can have a collection of points. So these points can themselves have some flavors, but I want these flavors to be not just say homology classes. I want them to be rather pictures or diagrams or maybe homotopy classes. So I really want them to be more than just we have in the case of polynomials or whatever else invariants say. For example, for Zyberg-Witten, we have again something like intersections of homology classes or evaluation of cohomology and cohomology or something like that. Okay, well, I'm extremely grateful to two persons who helped me a lot in preparing this talk. So first of all, these are Kim Sun-John and Kim Sarah. Of course, I discussed a lot with many other people, but well, I hope that soon I will be talking more about other pieces of this mosaics and possibly about the first steps, how to get from classical knots and knots on the cylinder. And for example, now we are working on knots on the cylinder with Kim Sun-John and Kim Sarah. And actually, whenever we have a sort of parity, I will tell more about that. We can do the things I'm going to talk about today. Well, so here is the main hero of today's lecture. Actually, I want to distinguish between some even objects and some odd objects. So actually, I want to distinguish between even crossings or odd crossings. And actually, the background is like that. So assume I live in some configuration space or moduli space of something. Well, I want to get some characteristic loops. These are not just characteristic classes, but I insist on having something like loops which count maybe homotopy instead of homology. So I want to go some way where possibly homology is trivial, but I want to have some homotopy. And assume I want to write down some words where I intersect some maybe characteristic surfaces or something like that. And in order to do that, well, I have to be sure that the things I intersect are somehow non-trivial. For example, what's the main difference between knots and links and why link invariant? I mean, the linking number appeared much before we had not invariance. Maybe because when we look at links, we can count crossing numbers. We can count crossing numbers between different components with signs. And for knots, well, it's not quite comfortable because of the first Reidemeister move. So, well, in some sense, virtual knots behave in a way very similar to classical links. And now I want to argue that in free knots, we can enjoy all possible ways of doing that, but we want to have something like odd things. And if we have odd things, they cannot just disappear. And actually, you can imagine that you have not just free links, but you can have whatever discrete things you like. So, well, some moduli spaces of PDE, but I don't want them just to disappear as crossings disappear after the first Reidemeister move. Okay, so virtual knots behave like classical links, and the simplest instance of this difference is the Gaussian parity. So we'll look at a Gaussian diagram and we'll look at a chord. This chord can intersect, or I better say to be linked with oddly many chords or maybe evenly many chords. And so in some sense, odd chords behave like mixed crossings of classical knots, and even chords behave like pure crossings between a component and itself. And the main difference being that mixed crossings cannot just disappear one by one. So an odd thing persists until it gets canceled with a similar odd things, maybe with some other sign. Okay, well, and in some sense, odd things behave like cats. Actually, now I'm teaching a course of lectures called Invariants and Pictures, and I have a book. So I think Son John can share this book with all of you. In the chat line. So this book is called Invariants and Pictures, and in some sense, I would argue that virtual knots and maybe some instances of virtual knots, maybe free knots with more or less generalization or simplification behave like free groups. So what do I mean here? Well, actually, I would be very happy to have invariants valued in cats. So why am I happy with free groups? Because if I have a word in free group, then we have a unique reducible representative of that word. And actually, this unique representative can be obtained by just simple cancellation of similar terms. So we can do it here and there. And finally, we can see that this minimal word sits inside any other word equivalent to that. And now I want to dream that we can have the same for knots. Actually, when I dream easily, this will not be true, but let's do something like that. Assume this cat is minimal in the sense that we are unable to do any decreasing Reidemeister move, or even maybe the third Reidemeister move. Well, we can decrease, but we can increase instead. So I mean that, this cat can pull his tail and make two crossings like here. And after that, we can perform some smoothing and see the initial cat inside the picture of the bigger diagram. So you see that K is obtained from K prime by a couple of smoothings. Well, of course, this dream does not come true immediately for classical knots. For example, we have a culprit knot, and a culprit knot is an unknot which has which is locally minimal but not globally minimal. And actually, now I want to argue, and I want to convince you that if we deal with objects I call free knots, we will have this principle, and actually it will appear in many other situations in topology. So this will be an overview talk when I will prove just maybe one collection of results devoted to free knots. Okay. And actually, I'm fond of this formula. So for me being lazy, I don't like many coefficients and many polynomial invariants, but I want to have a formula like this. So I want to have an invariant valued in graphs. And this formula will mean that if we have some graph which is complicated enough, then it realizes itself or reproduces itself. Meaning that if we have a graph, then we can construct a sort of bracket, which is similar to my parity bracket. If you haven't heard, I will repeat it. This bracket will be somehow similar to the Kaufman bracket in the sense that we are doing some smoothings. But on the other hand, it will have a great distinction that we don't smooth everything. So somehow we will have not numbers, but I'm happy to evaluate pictures in pictures. And here is the formal definition of the bracket. So I want to deal with Frankfurt graphs themselves. Actually, I can't do without any moves at all, but I will just stay with the second Reidemeister move. So graphs will be modulo second Reidemeister moves. And actually, well, I don't want to distinguish between signs. I can do it, and it's written many times. So I can get Kaufman bracket, and I even can get Khovanov homology with new gradings being pictures. But I just consider this form a linear space. And here is the definition of my bracket. So what does it mean? Actually, I look at even crossings and I smooth them either way. So in the way we are just doing for the Kaufman bracket. And I want to concentrate myself on only on smoothings which give me just one component. So I just completely disregard crossings having more than one, smoothings having more than one component. And I want just to count them as diagrams, maybe up to Reidemeister 2 move with the Z2 coefficients. So this is the formal definition of my bracket. Well, now a small remarks. Assume I have no even crossings at all. Then the bracket of k equals k. So then I have this. Then I have this nice formula. I'm looking for everywhere. And actually, the first situation I had was the reduced word, the reduced form of the word for free groups. And now,
Vassily?
Yes, do you hear me?
Did you, yeah, did you define even and odd? I know the definition, but I don't know if others do. So,
yes, just say it again. For Gaussian parity, Gaussian parity is defined as follows. I just look at a Gauss diagram and look at how many for a chord. I look
thank you. Okay.
How many chords intersect this chord.
Okay, thank you. I'm sorry, I missed that point. Thank you very much.
Yes, and actually we will see that there are much more parity than just this one. And actually, whenever we have a sort of Z2 homology, we will have some parity. I will write down some parity axioms here. And actually here you see if all crossings are odd, then the bracket of k equals k. And I'm happy with that. Well, unfortunately for classical knots, we don't have an immediate parity, so that that's why we have some things like culprit knots, and that's why we have to seek some further ways of drawing classical knots, or maybe drawing them on the cylinder as we are doing now with Kim Song-John and Kim Sera, or maybe doing some other things. And here is an example of an irreducibly odd diagram. So what do I mean by irreducibly odd? Well, I mean that we have no way to apply the second decreasing move, so that this diagram D is minimal, is locally minimal, in the sense that there is no way to apply Reidemeister 2, so we require that, and also there will be no way to apply Reidemeister 1 and 3, as we will see from axioms just in a couple of minutes. And you see, I'm fond of this formula. What does it mean? So this means that in the left-hand side, D here is a diagram of a particular diagram of a knot. So this is one representative of a dynamical object. So actually here I can take any other diagram of the same knot. Well, Reidemeister 2 is an easy thing. And here D is just one particular diagram with coefficient 1. So actually, by looking at this formula, I can think of all possible diagrams of D. And for example, I can say that any diagram of D contains D itself. And here is the first instance of how I disproved Turaev conjecture and how I started creating lots of invariants of free knots, flat knots, virtual knots, and many other things. So here is the Gauss diagram of the free knot drawn here. Actually, here classical crossings are just drawn by vertices, and virtual crossings are encircled as usual. And here I have 6 classical crossings. This means I have 6 chords, and actually they are all odd, okay? Actually, as we see here, no odd chords are parallel or adjacent, so there is no way to do Reidemeister to move. And actually, this means that this local minimal diagram has no is actually globally minimal because well, assume we have something and assume we have some. So this is the main principle. If a diagram is complicated enough, then it realizes itself. So in some sense, parity bracket is just the first instance of that, but there will be more. Not just coming.
Vassily, is that
Yes.
example of, is that the six the flower one, which
Yes, so this is the sixth flower. Can you speak more loudly?
yeah, is this the evening star? What do you call it? Never mind.
Well, so yes, so this is the Gauss diagram. So on the right, I have the Gauss diagram of what I drew on the left.
Yeah, sure. Okay.
Okay, actually for 6 crossings, I have, well, at least 3 such diagrams, I think. We're completely odd. And for 4 crossings, I have nothing. And 5 crossings is impossible for completely odd diagrams. So actually, so this is the main principle I want to demonstrate here. And the simplest variant of this principle is that if all diagrams are odd and there is no way to apply second decreasing Reidemeister move, then whatever diagram of K prime equivalent to K I take, then it will have a smoothing which is identical to K. This is just an instance of my picture with cats. Well, so why is it so? Well, because if I just take the bracket of K prime, I will see that it will be equal to the bracket of K, which is equal to K itself. But by construction, the bracket is just, well, something made by smoothing. So among smoothings of K prime, I will have something which equals K. So, well, actually, if free knots can be kept by some, going further, such results can be extended to some 2-dimensional things. For example, free knots have non-trivial cobordism classes, and actually, if we have some completely odd diagram which can be kept by a folded disk, then they can be kept by a disk in a simple way. So if we deal with a folded disk and want to consider it as a dynamics in time, we can say that time shall unfold what plighted cunning hides. I mean that if we can do something folded, then we can do something unfolded. This takes me so much far away, and it's a joint work with Denis Fedosseev. And actually, parity says that knots can behave like links. Just find a good parity. Where to take parities? Well, I can say a couple of words about knots in the cylinder, because in the cylinder we have a non-trivial homology. I hope that we will prepare the second talk for knots in the cylinder. And actually, whenever we have some, class of homology, maybe coming from whatever structure, complex, contact, or whatever, we can expect that we have, some hypersurface, which leads to some Z2 homology or something like that, and we can distinguish between even and odd things. So knotoids also work with parity, and so on. So now about immediate applications for free knots, which come for free. For free knots, and of course for virtual knots, because free knots are just a complete simplification of virtual knots. Say, if we want to see convertibility, then knowing that the bracket of K equals K, and having some finite, reduced knot diagram, which is not equal to itself, then K is not equivalent to minus K. Well, here I'm cheating a little bit, because in its simplest form, the bracket does not know the orientation, but we have some brackets like Kuperberg bracket and so on. And I wonder even maybe some number of colorings which Penrose found to be negative somehow. Maybe some number of colorings can be found to be not a number, but a picture. And actually, we know invertibility for mutation, we can have the same idea. Actually, if a diagram is not a mutant, then, well, the knot is not a mutant. And in a similar way, if we deal with words, we can say that, well, if a word is not palindromic, then it's not equivalent to its inverse or something like that. So today I will work with words more than with pictures, maybe actually some applications which potentially can cause some problems. For example, so I want to say a couple of words about a caveat for classical knots. And the caveat is that classical knots do commute, and virtual knots actually do not commute except, well, obvious cases like powers of the same or maybe classical knots. And free knots, I suppose they never commute. So here I will give some instances of obvious non-commutability, and actually an obstacle here when trying to do invariants of classical knots valued in free knots. Well, there will be some grain of salt saying that, well, our map should not necessarily be homomorphic. So if we want to make some group or semi-group, well, possibly we should take care of, well, getting non-commutative objects. If incidentally there are students for here and they want to have a problem for research, so here are some projects. Look at classical knots to loops in various modular spaces. So what do I mean? Well, we can consider a modular space of classical knots and assume we have something, for example, trisecants, quadrisecants, or maybe we can assume that we have not just classical knots, but knots with some specific structure, maybe Legendrian, simplicial, or whatever, or maybe modular spaces coming not from knots, but from some manifolds, and just try to look at such loops. And if you have loops, then possibly you can put some points which appear to be even or odd. And actually, there is a great chance that you will have, that you can write some words. And well, actually for Kirby calculus for manifolds, well, potentially it's possible, but here we will have to investigate further group theory. So this is just some problem to mention. Actually, possible further applications for two knots. Actually, we have some loops. For example, we can draw the picture with Möbius, with a picture with a Morse function, and we can go from the top to the bottom, getting a word, and specify our attention on something. As for other things which are already initiated, is something we started with 1J for manifolds with complex structures. And here actually some new things appear. Well, they are not new for me, but possibly they are new for some of you, possibly some of you hear about these groups for the first time. And actually, when dealing with classical braids, we can look at something of co-dimension 1, which behaves nicely, for example, triple points, and which give rise to morphism from the braid group to something nice. And actually, there is a whole book. Sanjon, please share the book with our colleagues. So we get highly non-commutative groups, and actually they have lots of epimorphisms to free groups, which gives us lots of easy invariants which are strong enough. So here I want to construct some non-commutative mathematics, and actually Well, in our attempt to replace homology with homotopy, we can say the following: assume we have some intersection between, say, some two manifolds of complementary dimensions. Assume we have some intersection points which are, in a certain sense, A, B, minus A, and minus B, and we can say that they cancel in a certain sense. Of course, here I'm talking about some eventual possibilities, but I want just to give the whole picture of where to put my concrete result to be demonstrated here. And well, instead of A plus B minus A minus B, I would like to say that, well, assume I have a tricky way of finding a path through these points, and this tricky way can be something like, well, A times B times A to the minus 1 times B to the minus 1. So I assume I can find a way to carry on. Assume I can make it non-commutative. Then I can have funny invariants valued in non-commutative groups. And actually, there are some instances of this principle, but I will not touch on them today. Okay, and actually, here I want to, after many discussions with Lou, well, there was a joke, I think, which is both nice and both very cute and notorious, that categorification corresponds to cats. Actually, by that I mean that if we have a picture of something, a picture of a knot, a picture of a manifold, a picture of a cat, then we can, well, instead of counting numbers or tensors or whatever, we can draw cats and count them. And for me, categorification in this sense can be more attractive than just categorification when we count just some dimensions of linear spaces. Actually, cats already appeared in my generalizations of Hovanov homology for various kinds of virtual knots when they appear as new gradings. But I think, well, between cats we can have cobordism, which will be two-dimensional, and still it will be just the tip of the iceberg. So I think there will be much more instances of the categorification. Well, just let's return to our main hero, free knots. And actually, I want to get something valued in free groups. And for free groups, we have something for free, and we have reduced words. And in some sense, this reduced word can be thought of as the main invariant of all words in this class. Okay, and for knots, I would be very happy to deal with just second decreasing Reidemeister moves and nothing else. And if I can do this way, then I can get to the minimal representative just by using the diamond lemma. And actually, I can get rid of the first Reidemeister move and the third Reidemeister move because, well, I can have such magic brackets. This is not the only bracket I have. We have more. Actually, here I want to give some advertising. So every Friday I teach a course in invariants and pictures. This is a bilingual course, both in Russian and in English at the same time. Well, here are the steps towards the goal. So I want to get elements of a free group. I want to concentrate on and give exact formulas and some proofs. And well, here I would like to say that I have long free knots. So I just cut it and pull its end to the infinity. And for compact free knots, I will have conjugacy classes as expected. And again, this will be something like free group. well, maybe not completely free, maybe just a free product of some Z2s, but for me, it's good enough. Well, and the general plan will be, again, try to find some homological conditions, well, and put some labels and make them not commuting with each other. So I want to have something one-dimensional, and I want labels not to commute. Okay. Well, and actually, one more thing I have to mention is that I really need odd objects, because, well, if you just, for example, I just count classical crossings and I assume I want to associate letters to something like classical crossings, then the first Reidemeister move can oh, excuse me, my mouse is too quick, maybe. For a classical knots, I can get a painful relation like that. So this is, well, I don't want to have it for the first Reidemeister move. I would better have this relation, which more or less comes from the second Reidemeister move. So, well, in order to avoid these things, I have to avoid first Reidemeister move, or maybe cusps, or maybe some vanishing homology classes. So I really want to have something odd. Well, and again, from homology to homotopy, from abelian groups to free groups. Well, and now I start some serious definitions, rigorous theorems, and so on. So now I want, yeah, my mouse is avoiding the cat. Right, thank you. Well, and actually, I want to give some 3 steps of constructing some invariant. So first, I would like to construct this invariant as a bare count. Actually, here I have to give credit to Lou, who maybe was the first paying attention to the parity of crossings, and he suggested some parity right. Actually, if we have a virtual knot, we can look at the right number at just odd crossings, and they cannot get canceled unless with themselves. So we have to compare some odd ones. Odd ones cannot disappear at the first Reidemeister move. Okay, and first I would like to give some integer value, not for virtuals, but for free ones. And actually, this says that odd things can have some signs inside them. So possibly not quite visible signs, but maybe some signs that we can extract from somewhere. Well, and then the second step will be to transform this invariant to be valued in some group. Well, I'm cheating a little bit. It's not the infinite dihedral group, but, well, in some higher sense, maybe in Gromov sense, this is similar to this group, and maybe you see that B prime is nugatory, but let's stay for a while here. And also, historically, these 3 points, the order of these 3 points is incorrect, because first of all, I was really eager to find an invariant of free knots valued in free groups. Well, at least in some non-commutative groups, and actually I constructed an invariant here. But as you will see in a moment, looking at the calligraph of this group, it's nothing but Z2 star Z2. And Z2 star Z2 is almost the same as Z, in the sense that it has a finite, it has this infinite cyclic group as a finite order subgroup. And actually, if I look at that, if I stare at that very carefully, I can see that everything can be reduced to that. And after that, I will be very much disappointed, because I realized that my invariant, well, is far from being genuinely commutative. But, well, if I can get rid of just these relations, but by using just some tricks with words, renaming letters and rewriting words, then I can get a genuinely non-commutative group. Well, and actually, from the algebraic point of view, we can say that there are some actions of Z2, and we can get one skew product, two skew products, but I don't want to say much detail about that. Okay, so again, about the definition, possibly should be given much before. So chords are linked if their endpoints alternate, and we can write this as a scalar product like this. And a chord is even if it intersects evenly many chords, and odd if it intersects oddly many chords. And now I want to formulate the four properties of parity, and actually these four properties is the only thing I need. And in fact, these four properties can be thought of as a collection of axioms the parity should satisfy to give us a lot of things like parity bracket, and even something I called parity projection, which was the main thing in the construction of the projection from virtual nodes to classical nodes. So actually for each virtual node, there is a classical node living inside that. And actually, here are the axioms. So a chord taking part in the first Reidemeister move is even because 0 is an even number. This chord intersects nothing. Well, if two chords are canceled by a second Reidemeister move, then they have the same parity. Well, because they are just adjacent, they intersect the same things. Well, and actually, well, here I should have given given the third axiom. Well, in another way, excuse me, I forgot to say about one crucial axiom that if we have three chords, taking part in the third Reidemeister move, then the number of even chords among them is, or the number of odd chords will be even. So either they're all even, or there are two odd ones and one even one. Well, and actually the fourth is not an axiom, it's just a property, okay? Well, and now I want to give my invariant. I want to define it precisely. So what do I do? Actually, here I give types and sorts, but I suggest you better to look at what I call sorts. Well, actually, types and sorts appear because they appeared in different papers differently, and I just don't want to contradict any of the papers, so I want to keep notations as it appeared first. Well, so well, I want to distinguish between odd chords and even chords, and here in my diagram of a long free knot, all even chords are red. And now I want to look at black chords, which are all odd, and they can be of the first type if they intersect evenly many even chords. Otherwise, they are on the second type. So I use one bit of information, but now I use sort, which means that I use 2 bits of information and take their sum mod 2. Actually, here is a word here is the word I want to associate to that. Actually, A's are always ends of even chords, and B and B prime are associated with respect to the type, I think. Well, and actually, I want to define my invariant L as just twice the number of odd chords of the first sort minus twice the number of the odd chords of the second sort. Twice because, each of those chords has 2 ends. Well, and actually, we have this invariance theorem, which can, students which carefully analyze the Reidemeister moves can immediately see that it happens, and actually the sort of the chord persists the same, although the type can change. So the sort persists the same. Actually, if two chords are cancelled by a second Reidemeister move, then they have opposite sorts. Also, if we look at compact knots, then this invariant can change its sign. Well, actually, this invariant was the first sliceness abstraction for free knots, and in some sense, this is a tricky way of getting signs which cannot be cancelled, unless with each other. Okay, so this is the bare count, the first thing. And now, now I want to construct a group. For this group, I want to do the following. I want to write down a word. I want to associate it to a long Gauss diagram, to a long free knot. And I do the following. I follow the orientation, and even chords give me A, and odd chords given B or B prime, depending on the type. So for example, here I have the word BA, 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 B, B prime, and so on. So here is the word. Well, and now I want to understand the rules of the game. What happens if I apply Reidemeister moves? And I think I see that something very non-commutative happens. And actually, here is the first instance of the Cayley graph. Here is the Cayley graph. Actually, in this Cayley graph, of course, my generators are all inversions. I have just this railroad. So here is the unit, and A squared equals 1, B squared equals 1. And you see the word I associated with my knot is just this snake, which goes from here to here. And actually, we see that this word, doesn't have so much inside it. Well, actually, it has only length 8. So this is more or less plus 8 or minus 8, depending on, actually, if you start from another point, you will get 8 steps to the left. And actually, you can't get to from the bottom line to the top line because just the number of A's is even. And here is just the formal theorem. And you can see that Reidemeister 1 gives us only this, and Reidemeister 2 can give was either variant of those three, and finally Reidemeister 3 can give us one of those. Okay. And this is exactly the definition of the relations. Of course, in this group, I can express B prime in terms of AB, but for me, it's more convenient to do so. Well, and actually, the third step is, as you see that, as for the Reidemeister 2 move, B can occur in that. But for Reidemeister 1, actually, I can't get B. And so the question can be, can I get rid of the relation of B squared equals 1? And actually, I can. And so that's what I'm going to do. The idea is as follows. I want to treat B in different positions differently. And actually, if I have a word, I can say, okay, this B appears in even positions, or that B appears in odd positions. When I say positions, I mean both ends of the same chords. So this chord is odd, so this means that it intersects oddly many chords, and so this means that the parity of both ends are the same. So for example, here I have something like odd chords. So here an odd chords appears for 1 and maybe 5, 3 and 7, 8 and 10, 12 and 14. So the same parity for both ends. Well, and here It's easy to check that right-master move give rise to that and nothing else. And you see here we have no B prime equals 1. And that's why we see that the Kelly graph of our group is like that. Well, possibly we should have put some arrows for B's, because B is not is not an involution, and B is not a reflection anymore, so B squared is not 1. But here is a group, and of course it has an exponential growth. And I think that all of us, we can easily imagine that whenever we have right and left structure, or whenever we have over-under crossing structure, these groups will be more and more complicated, and we will have some flowers to give to our cat. Okay, and so we have this psi of k, and so we just replace B prime with B prime to the -1 and B with B to the -1, and actually there is almost nothing to prove here. Just check right-master moves and nothing else. So the proof comes from the formulation. So here we have to give an accurate formulation of the definition of our group. Well, in this example, we have this word, and what we had for our initial group in G. So we had only one railroad and actually one rail. So this led us to nothing but a distance 8. And in this group, we have to climb this tree, and so you see it's just a piece of our path. So actually we don't have actually it will have length 14, I think. Well, so we couldn't have drawn it up to the very end. Well, more or less, this was the main theorem of today's talk. And actually, for G, we had nothing but just this thing to the 4. And actually, this thing is just the generator of the Z group, which is comparable with the initial group, is a finite index, actually index 4. And now we see that invertibility, or whatever mutation you invent, in our powerful group C, we can have this. And actually, next goals will be to do such things for classical knots in 3 manifolds, whatever. We have to find appropriate parities, and actually we do have for the cylinder, and this will be maybe number 2 step. And actually, more or less, obviously, we see that 3 nodes do not commute. And actually, we almost immediately see that from the group G prime. So we have to construct these things. So K1 sharp K2 is not K2 sharp K1. And if we do that, then in G prime, we more or less achieve the goal. Nevertheless, when we had only G, it was quite complicated, because more or less we had just this generator key B prime to some power. So actually it has a very large commutative subgroup. So there was almost no chance to prove any non-commutativity result. Actually, I suppose that for 3 knots, there is no commutativity at all, except, powers of the same. And, actually, this was proved to be the case for virtual knots, but not the power of the same, but maybe plus some classical knots. And for 3 knots, I have an almost complete classification, but there is still some minor gap. But anyway, from that, you have a lot of results for virtual knots immediately. Actually, further possible generalization to use parity hierarchy In fact, hierarchy means the following: you can delete odd chords, and some previously even ones can become odd, and so you can distinguish between even ones. This makes our life fun. And the invariant, well, it's a sliceness abstraction for free knots. However, we got quite stuck in estimating the slice genus, and actually, more or less, the problem is as follows. So having value to be having value 8, it can get split into 4 plus 4, and then 4 becomes minus 4, and we get 0. So I expect this highly non-commutative invariant can give us many approaches to that. So it's not yet done. Of course, for virtual knots, we have a lot of things. So just some further problems we're interested in. For example, can we project? Actually, parity can prove some results that some small category is a subcategory of a large category, something like classical knots embed into virtual knots, because classical knots are even with respect to whatever parity, and virtual knots can be odd. And there is a way of projecting. And actually, we can do that for braids also. But actually, parity, planarity, and homology methods can give rise to much more. Something was done for a genus. For example, the slice genus of classical knots is always realized by classical diagrams. So this is made by using parity projection for 2 knots. We can dream in the following way. Actually, whenever something is not good, classical knots are good because we can draw them on the plane. And if something is not good, that possibly it's not drawable. Actually, we can have some instances because some cycles do intersect in the Z2 homology of something. And actually, homology yields some badness and some projections. This is more or less the same. So here is a list of references. And here is my last paper, which was the last day of the last year. We have books, something like that. We have cobordisms. And don't we have my, okay, and as for the last book of mine, it is in the chat line. And I think I fit into the, into an hour and a half, and I thank you very much for your attention.
Well, thank you, Vassily. Are there any questions? I just wondered how you could define parity for a knot on a cylinder.
Well, for knots on a cylinder, the parity can just come from homology. So if we have a path on a cylinder, then we have some winding number. Assume for simplicity that the total winding number is 0 or even. Then at each crossing we have 2 halves, and they are of the same parity. So this is a parity. Another way of defining parity is some number of half twists. For example, we can draw not only crossings which are on the same side, but we can also draw crossings which are on the opposite sides. And actually, then we can say, okay, crossings on the same side are even, and crossings on the opposite side are odd. And actually, this corresponds to the angle pi. And in fact, there are much more things. For example, we can look at pi over 2 pi over 3 and many other things. but this is well, a work in progress, and I think in a couple of weeks or maybe a month, we will have exact theorems. But the parity, well, once we have homology, we immediately have parity.
Okay, that's interesting. So, are there any other questions?
Yes.
Ken,
Hello. Am I coming through?
Yes, yes,
coming through.
yes.
You mentioned your weekly course on invariants in pictures. I wonder if there's some way we can tune that in.
Oh, yeah, sure, of course. Sanjan, please give the link, and please give the link to KTRT. Yes, we have many events, and I would be very happy to invite you to our seminars.
There's that Friday talk you said on
yeah, Friday. It's very good for the West. Nevertheless, well, I mean, in Moscow it's evening, like today, and well, in the West it's afternoon, and in the U.S. it's even earlier. But nevertheless, some people from China and Korea usually attend my course after the midnight.
Well, I'd really like to follow invariants of pictures because I reviewed your book for ZBL and I did a terrible job of it, and it's time for me to learn some more about it.
Yeah, I would be, well, of course, it would be an honor of mine to, it would be an honor of mine to see you, of course. Well, sure.
I'm not that good with computers. I just wonder how I can find it when.
Oh yeah, yes. So Sonja just
Ken,
Sonja will guide you. Of course, here's the link, and of course,
good.
Just write to me or just write to Sonja, and I will be.
I can send Vassily's email address to you, Ken, if you want.
Perfect.
Is the YouTube link a recording of your lectures?
Yes, maybe except for the last one, which I have to polish a little bit. Yes, maybe the first 5 or 6 lectures are already there.
So maybe that would be fine as a reference.
Well, okay. So yeah, I think Sonjon can give it as well. But anyway, we will send it just upon request immediately.
Thank you.
Vasily, be sure to send us the slideshow that you just used, and we'll put it in our Dropbox so that everybody can use it.
Yeah, sure. I will be happy to share it with all my colleagues. And and again, it's really great honor for me. So we have all sorts of classical papers, of classical books. And actually, it's my first instance when I talked to Professor Rourke, to Professor Rolfson, and of course to Professor Lomonaco. So of course I know Roger and Lou and Scott. But it's a great honor for me to see all of you.
Well, that's nice to be honored, and we're honored to see you.
There, we'll second that.
If there are no more questions, let's give Vassily a clap.
Thank you very much. It was really a great pleasure.
Next week we have a talk, I think, on Kovanov homology. Is that right? I can't remember. Anyway, we'll send around details about it. So possible, and I think after the next talk we'll have an Easter break.
What's the time? So our time shifted with respect to yours.
We will be up to date with you. So I will send it as GMT.
So 5 p.m. or 6 p.m. GMT.
It will still be 5 p.m. GMT.
That's going to be noon, I think, our New York time, right?
It'll be what it used to be before because we're a week behind in changing.
Actually, I even don't remember whether we shift whether we shift to the summertime, because maybe every 5 or 10 years there are new regulations in Russia to shift or not to shift.
Okay, well, thank you again, Vassily.
Thank you very
And,
much.
if there are no more comments or questions, I will end the meeting now. So, bye, everyone.
Thank
Bye.
you.
Thank you again.
Bye.